to speak will be Peter Zeman, currently Hagen, and Peter will talk to us about NPA hierarchy in the context of different games related to graphs.
Yes, thank you. So this work is a bridge between quantum information and combinatorics. And first I would start by a little story how we came to this project. So Prem, the PhD student, was attending a course on convex optimization during his PhD studies. And so we are working with David, who is a co-author on the result about quantum isomorphism, bridging it to homomorphism counting of planar graphs. And Prem, as a homework project, took upon himself to study about the NPA hierarchy as a part of the convex optimization course. And then his idea was to, let's just try to apply it to the quantum isomorphism game, and the graph isomorphism game, and let's see what happens. And this is what happened. So apparently something good can come out of attending a course. So yes, so I will start with a motivation from combinatorics. So let's just start by some basic definitions. So we will be concerned with graph isomorphisms and homomorphisms. So a graph isomorphism is a bijective map between the sets of vertices of two graphs that preserves adjacencies and non-adjacencies. So here is a small example. So these two graphs are isomorphic. Homomorphism is a similar concept, but now the map does not have to be bijective, and it only requires to preserve the adjacencies. So, for example, here is an example of a homomorphism between two graphs, where on the left we have a cycle on 7 vertices, on the right we have cycle on 5 vertices, and the vertices are mapped from left to right according to those colors as depicted. So some vertices can go onto one vertex. And an important theorem in combinatorics that connects homomorphisms and isomorphism relation on graphs is a famous theorem by Lovász. And this basically says that you can characterize the isomorphism relation by counting homomorphisms from graphs from some other graphs to your two graphs that you are considering. So by this hom fg, we mean the number of homomorphisms from a graph f to graph g. And now this naturally leads to a notion of homomorphism indistinguishability. What happens? So now here in theorem of Lovász, we can use all possible graphs, but what happens if we restrict our graphs to something, let's say, more simple than all graphs? And then this leads, and the question is like, so if in the case of all graphs we have the isomorphism relation, what relations do we have in case of the restricted classes of graphs? So more formally, two graphs are homomorphism indistinguishable, denoted like this, with respect to some class of graphs, a calligraphic F, if for every graph we have the same, if for every graph from that class we have the same homomorphism counts. And now, this is a very studied problem, so here is just a few of the examples that are known. So the first line is the already mentioned theorem by Lovász. So if we take all graphs here, then the homomorphism indistinguishability corresponds to isomorphism. But you can take various other classes of graphs, like you can take cycles and paths, and this will correspond to some cospectrality of the adjacency matrices. So that's again some kind of relation on the graphs. Then you can take trees, which is the so-called fractional isomorphism. So isomorphism can be expressed by a permutation matrix. So two graphs are isomorphic if the adjacency matrices commute with some permutation matrix. And fractional isomorphism, a similar thing, but you replace a permutation matrix with a doubly stochastic matrix. Then we have here, for example, I want to mention tree width at most k. So tree width is some kind of a graph parameter that tells you how far is the graph from a tree. So trees have tree width 1, and so on. And for this, there is so-called, the corresponding relation is being indistinguishable by k-dimensional Weisfer-Lehmann algorithm, which is some kind of canonical procedure to compute invariance of graphs. And now, the sort of like, after seeing these classes, the most natural class a person in combinatorics would consider are planar graphs, simply because planar graphs are considered as like one of the first classes of graphs in various kind of applications and algorithmic problems and so on. So, and this naturally leads to the seminal result by Laura and David, and the corresponding isomorphism relation is the quantum isomorphism, and this is how this topic is linked to quantum information theory. So even if you come just for the combinatorics point of view, you sort of naturally arrive to this, because maybe someone could argue that we're just putting words quantum in front of everything, and that's because it's interesting. But no, if the planar graphs are a natural thing to consider, and we naturally arrive to quantum isomorphism. And this paper is about relaxing quantum isomorphism. So similarly as for isomorphism, isomorphism problem is somehow a hard problem. It's the interesting thing is to find relaxation for that, so that which are more easily, let's say, computable. So quantum isomorphism is undecidable problem, so also somehow very hard. And the interesting thing is to find relaxation of that and see whether this relaxation can be decided, or even decided, or even like efficiently decided. And this is the case indeed. And we define a certain subclasses of planar graphs for which the homomorphism indistinguishability relation considers to a certain NPA hierarchy being feasible for the graph isomorphism non-local game. Okay, so this is sort of the main theorem. So this NPA hierarchy provides a relaxation. We'll get into more details in that. Provides a relaxation for the graph isomorphism games in form of semi-definite programs. And the kth level of the NPA hierarchy is feasible if and only if there exists what we call level k quantum isomorphism map between graphs, and if and only if the graphs are homomorphism indistinguishable over this class pk, which we define. So let's go to the graph isomorphism game. We have already seen this, but let's recall. So Alice and Bob want to convince a referee that two graphs are isomorphic. So we assume that the graphs are of the same sizes. So, so the referee asks questions. These are vertices G and G prime. Alice and Bob respond with vertices H and H prime. And to win, the players must respond H and H prime, such that the relation between H and H prime and G prime is the same. So if they're adjacent, they have to be adjacent, non-adjacent, non-adjacent, and so on. So two graphs are isomorphic if only if the classical players can win the game. Now, the quantum isomorphism is defined by letting the players be quantum, letting them use a quantum commuting strategy. So Alice and Bob share a quantum state, and so when Alice receives the vertex G, she performs a projective value measurement, and this consists of some matrices, as we know it, and we'll define it precisely a little bit later. And Bob similarly has his own measurement, and in this type of strategy, we assume that these matrices commute, and as the commuting measurement strategy is defined, there is some probability that the players respond H and H prime for the questions G and G prime. And so we say that there is a quantum isomorphism if and only if they can win, if and only if the quantum players can win the game. And here is an example of graphs that are quantum isomorphic, but not isomorphic. So there are very similar graphs, and this construction is based on linear system games. I think this was one of the first constructions of such graphs. So there are graphs that are isomorphic, but are quantum isomorphic, but not isomorphic. So now we arrive to the NPA hierarchy, which is a hierarchy for each non-local game and commuting measurement strategy that provides us with some hierarchy of semi-definite programs that provide some relaxation. So let's just recall the definition in general. So in general, a non-local game is a six-tuple where we have some questions, x, y, and answers, a, b, corresponding to Alice Bob. We have some probability vector that gives us with what probabilities the questions are drawn by the referee. And then we have some predicate which tells us whether for given answers the player won or lost. So now to think about NPA hierarchy, it's good to think about the strategies being represented as matrices. So we can encode a strategy into a matrix, which is a linear operator for this kind of space to this kind of space. And the value, formally the matrix is indexed by the tuples, by the two tuples, but it's usually denoted like this to sort of mimic the notation for the predicate. And so basically the entry of the matrix represents the probability that Alice and Bob will answer the questions x, y with answer a, b. That's it. So, and then you can work out that the probability that the strategy M, represented by the matrix M, wins the game is given by the following, which is just comes from the, straightforward computation. And we can in fact also represent the game as a matrix. So this operator K represents the game in the following way. And then in fact, the probability that M wins the game is given by this inner product. And then to find the maximum probability, we will just have to take a supreme over all such matrices. So just an example, so suppose that our questions and answers are just 0, 1, and then there are these 16 possible deterministic strategies. That's not hard to work out. And then, for example, the CHSH game represented by an operator yields this kind of matrix. And then one can see that the classical value of the game is just 3/4. If you somehow go through all of the inner products, then you would be able to see that. Okay, so the NPA hierarchy, for that we need the commuting measurement strategy. And so just to recall, the commuting measurement strategy is represented by the matrix M, as we decided to do it. If there is a Hilbert space, a unit vector, and a projection operators for every x and every y, we have such a set, and they have to satisfy the usual conditions that they sum up to 1, the p's and q's. We require that the operators commute, which is basically relaxing the tensor structure from entangled games, and the probabilities, the entries of the matrix correspond to the probabilities that some answers will be given to some questions. And then the commuting measurement value of a game is just the supremum over all such strategies. So the C here is the class of all commuting measurement strategies, so the class of all matrices that satisfies these conditions, and K is the matrix representing the game. So now the intuition behind the first level of the NPA hierarchy is the following. So we would like to capture these numbers that are in this matrix. We would like to somehow capture them. So to that end, we consider all possible vectors of this form. So we take the unit vector, which comes from the strategy, and we take the measurement operators, and we consider all possible vectors like this. And we take the gram matrix of that. And to have a nice notation, we can denote it. So we can denote the labels. So here we take the disjoint union of the x and a, which are the questions and answers for Alice. Likewise, y and b, and we take the empty string, which somehow corresponds to the vector u. So we take this kind of set of strings, and this will be the index set. If you think about it, you can index the gram matrix by this kind of strings. And of course, the matrix will contain a lot of strings that we are not interested in, but there will be, of course, those that we are interested in. So suppose that R is such a matrix. So it's R is such a matrix, such a gram matrix. So it's positive, semi-definite, and so we can now observe what is true for this matrix and basically just translate the conditions from the definition of the commuting measurement strategy into the conditions about this matrix. So let me just go through this more quickly. So there is some condition corresponding, condition on the matrix A corresponding to the fact that the vector U is a unit vector from the strategy. We have some conditions which look complicated, but they just correspond to summing over all the operators in measurements. So summing over all operators in the measurements is the identity. So this is basically expressed by these kind of conditions. Then we know that these P's are mutually orthogonal and also Q's. So this is captured by the third condition. Then we know that the P's and also likewise Q's are projectors. So they have to square to themselves. So this is captured by this condition, and the last conditions capture the commutativity of the operators of the measurement. So now you can define that the class C1 contains all the strategies, all the matrices M that satisfy for which there is that kind of matrix that we just described. Such that the entries correspond to that matrix, and then you can basically, so that's a class of strategy C1, and then you can bound the quantum commuting value by just going through the matrices in C1. Okay, and then one can define a Hermitian operator. So this is just by encoding, taking the matrix corresponding to the game and encoding it in a Hermitian operator. And then we can even get that this direct product K with M, which we had before, can be represented by this, which is already giving us a semi-definite program. So in this semi-definite program, we would optimize this inner product HR over all positive semi-definite R, satisfying the constraints that we have had above. So this is sort of like the intuition behind the first level of the NPA hierarchy. And now, then we go to the next levels, is just then, instead of considering these just, let's say, strings of length 1 that we have there, we would consider strings of length K. And so then we could consider these operators R indexed by this kind of strings of length K, also getting a lot of redundant entries, but also capturing what we want, satisfying some conditions similar to those that were listed. And then we obtain the class CK containing all strategies for which there exists such an operator, admissible operator R. And then we get a hierarchy of classes like this, which is the NPA hierarchy. So we have like C1, a superset of C2, superset of C3, and so on and so on. Everything contains the class C. And the theorem is that this kind of hierarchy converges. So if M represents a commuting measurement strategy, then M belongs to this class CK for every K. So, or you can view it as an intersection of a countable intersection of all those CK. Okay, let's go back to the isomorphism games, and sort of to formally, now we want to somehow apply the NPA hierarchy to the isomorphism game, and to sort of formally state it, I would need to go into more formalities about the strings. So this is just, consider this just to be a visualization that somehow if we apply this NPA hierarchy to isomorphism games, we get a definition like what is the certificate for the kth level of the NPA hierarchy for the GH isomorphism game. So you can somehow see that it's again some kind of matrix R that satisfies some conditions. And the point is that the GH isomorphism, so this is somehow the convergence of the NPA hierarchy for the graph isomorphism game, which somehow needs a little bit of an extra proof, but it's very similar to the convergence of in general. So we have that the GH isomorphism game has a perfect quantum strategy if and only if there is that kind of a certificate for each of the levels of the NPA hierarchy. And so now we have this feasibility certificate, and we want to somehow translate it. We want to get to the homomorphism counting. We want to go to graphs. So to that end, we will be constructing a completely positive map. So the idea here is to use the principal submatrix of the certificate for the kth level of the NPA hierarchy as the Choi matrix of a linear map, and show that this is some kind of level k quantum isomorphism, which we will define. And conversely, we will then we show that the Choi matrix of a level k quantum isomorphism can be reconstructed, can be used to reconstruct a certificate for the level k of the NPA hierarchy. So we have a solution for the kth level of the NPA hierarchy for the GH isomorphism game. The principal submatrix of R is indexed by this kind of set. So we have there the vertices and of the two graphs and the k-tuples of those, and then we have a linear map between these matrix algebras to be the linear map with the Choi matrix defined like this on the principal submatrix. And the idea of this is that we want to translate those conditions that we get from the NPA hierarchy on the certificate to some conditions on the completely positive map. And to that end, we use so-called bilabeled graphs, because we also need to translate it to graphs somehow. So now I would like to define this. So a k bilabeled graph is just a graph where you basically take these k-tuples of vertices which play some kind of a special role. So so you just take a graph and you take two k-tuples of vertices. So this will be what we call input and output. And the idea of this bilabeled graph that we sort of like to compose them and build larger graphs out of them. And these operations, how we put them together, will correspond to some matrix operations that will represent counting homomorphisms. So like example here is K4, just a complete graph on 4 vertices, and you just select any k-tuple so they can be repeated on one side, on the other side, so it's just really any k-tuple. And here is the example. So here is this drawn, so we have this K4, and this is the input labels. So 1, 2, and 2, 2 are the input label, and here we have 2 input labels and 2 input labels, and so output labels correspond to the vertex 2, and input labels to 1 and 2. And the way we draw it, sort of like to make the operations on the graphs understandable, is that so these input labels, this is the first input label, this is the second input label, and in that order we draw them on the left from top to bottom. So this is the first input label corresponding to vertex 1, this is the second input label corresponding to vertex 2. Likewise, on the other side, we have the first input label, output label, corresponding to vertex 2, and that's why we draw it here on top, like on the horizontal line together with the first input label. And similarly, the second output label also comes from vertex 2, and we draw it here. This is not so important, but this is just to make somehow the operations pictorially more understandable. So, and we say that this kind of bilabeled graph, so a graph with this kind of wires, is planar if it can be drawn with no crossings. That's quite natural. So,
sorry, are there crossings allowed in the wires, or?
Yeah, I mean, this is a planar graph, so this underlying thing should be planar, and I think, yes.
No, you can't cross the wires.
You mean like the wires, like here the wire crosses the edge, or what do you mean?
I mean, I know what a planar graph is,
right.
But in the drawing of a bilabeled graph, is it important that
Yeah, the wires do not cross. Yeah.
So this drawing is not planar. Maybe there's a different drawing that is planar, but certainly this
yes,
drawing.
yes.
Okay, sorry, thank
Right. Right, and we want to now represent the counting of homomorphisms by some kind of matrix representation. So here we have this kind of matrix representation. So we have a bilabeled graph F, FUV, with the input and output labels, and so the entry of this matrix entry of the matrix is labeled. The first part is labeled by G1 to Gk, so by a k-tuple, and the second one is labeled similarly, and this corresponds to this quantity, this number of such homomorphisms that satisfy the following conditions, right? So map the input labels on these vertices Gi, and map these output labels on the vertices on the vertices Gi prime. So then the homomorphism count from F to G is the sum of the entries. And here is a good example that if our graph is A, so A bilabeled graph with K2 with 1 and 2, then this will be just actually an adjacency matrix, because we can map an edge to an edge. Right. So we have some operations of this bilabeled on these bilabeled graphs that will then also correspond to operations on the corresponding matrices. So let's go through them. So we have this kind of so we have two bilabeled graphs, F and F prime, and this is the series composition. So pictorially, you just take these two graphs and just basically combine them, connect the wires as they appear on the picture, and you get the resulting graph. And the corresponding operation on matrices is the multiplication. And here is a more concrete example. You could work it out that by taking a series composition of these two graphs, you get this one. Then another operation is parallel composition. So here you can think of the parallel composition basically just taking one graph here, which is a matching, and taking this cycle and just putting them on top of each other. And you get this kind of ladder. And the corresponding matrix operation on the homomorphism matrices will be just the entry-wise product. And we have some more operations like transposition, cyclic permutations. So cyclic permutations somehow permute cyclically the wires, and transpositions flips them. And so these are, I don't have picture for those, but that's not that hard. So then we finally get to the definition of this class of graphs, pk, that we are interested in. And we already seen this graph. So this was the cycle, and this was the matching on the previous slide. So this we define it as a union of several classes. So we take this QKP to be the set of all minors. So graphs obtained by deletion, contractions of deletion and of edges, and vertices, contractions of edges. We also have a definition what exactly is a bilabeled minor. So here you take QKP to be the minors of the cycle, and QKS to be the minors of the matching. And let's define QK to be the union of those. There is a reason why we have to define this separately, and the class pk is then the class of all kk bilabeled graph generated by these elements of this qk, which we have as an atomic graphs, by series composition. And now there is only parallel composition with the elements of qp. That's why we have to split them. So the parallel composition is only allowed with qkp. The reason is somehow that if we allowed it, otherwise it would violate the planarity. So we need to preserve the planarity. Then we can do the transpose and cyclic permutation. So this class of graphs that will for which we will have the homomorphism indistinguishability relation is the class of all planar graphs that are generated in this way. And it's actually true that there will be planar graphs. So and then the boldface class is the bilabeled graphs, and the regular PK is just without the labels. And finally, we can define a level K quantum isomorphism map. So this kind of map is so we have a linear map from this kind of matrix, between this kind of matrix algebra is a level K quantum isomorphism if it satisfies certain conditions. So it has to be completely positive, unital trace preserving, sum preserving, and then it has to respect those operations that we had. And so such map will satisfy that the corresponding matrix for a graph G is taken to the corresponding FH for all bilabeled graphs in this class that we define, this PK. And the existence of such map implies the homomorphism indistinguishability over class PK, and there is also a converse. So this way we arrive to the original stated theorem that for the kth level of the NPA hierarchy, the GH isomorphism game, so the kth level of NPA hierarchy for GH isomorphism game is feasible if and only if there is this level K quantum isomorphism map, if and only if G and H are homomorphism indistinguishable over PK. And as a corollary, we get also the result of Laura and David, and so this is somehow from the convergence of the NPA hierarchy. So we want to show that the two graphs are quantum isomorphic if and only if they are homomorphism indistinguishable over this class P, which is the union of all of those PK. So to see that, we somehow need to show that the union of all of those PK that we defined is actually the set of all planar graphs. And yes, so we have to show that this P is a set of all planar graphs. And the one inclusion is that okay, so the generators of this PK are planar, and somehow these operations preserve planarity, so we can argue that. So that is the one inclusion, and the other inclusion is that this class PK is closed on minors. That all of the other classes are closed on minors, and we can show that the class PK contains the K times K grid. So we can generate this K times K grid, and it is well known that this kind of K times, like every planar graph is a minor of a sufficiently large K times K grid. That's a well-known thing in combinatory. So this is how we can do it. So we have these atomic graphs, right? This matching, this cycle, then using parallel composition, we can construct this kind of ladder, which was already shown, and then using a series composition, we can construct the grid, and that's it. So every planar graph is a minor of some K times K grid, so the union of all such PK will contain all the planar graphs. So some final remarks, and so in fact we do not know much about these classes of graphs. We just have these generating graphs. We just have those operations. We know some bounds on the tree width of those graphs, which I said is some kind of parameter which tells you how far is the graph from the tree. But in fact, we do not know much about them. But thanks to this bound on the tree width, it's actually non-trivial, but thanks to this, we are able to get a randomized polynomial type algorithm that tests whether the kth level of NPA hierarchy for the GH isomorphism game is feasible, which is kind of interesting because if you take all the planar graphs then the homomorphism indistinguishability over that is undecidable, and thus also quantum isomorphism is undecidable, but these level K relaxations, you have polynomial time algorithms. And that's where I would like to end.
Thank you very much. Any questions or comments?
So in the NPA paper, they have this rank loop condition, which says if the rank parametric rank doesn't go up, if you go up in the levels, then you get some finite dimensional quantum strategy for the game. Can you say something about this for the isomorphism?
I'm not sure. I'm not sure. Sorry.
No,
But maybe. Yes?
Try doing a parallel thing for the quantum chromatic numbers. So for each level K hierarchy, you could have chromatic numbers of the graph.
Yeah, we have not tried that, but it's definitely a nice thing to try. I think it would be interesting. Yeah, we did not get to, but certainly this can be applied to various things and try to analyze what we get for each level. So that's maybe certainly interesting, unless there is some previous result about it.
What's piece of one?
Sorry?
What's the class piece of one?
Oh, piece of one. You mean the P1?
Yeah.
Yeah. That's a good point. The class is pk for k equals 1. We can say that those are outer planar graphs, which are a special class of planar graphs where all the vertices can be drawn in a circle and all the edges somehow go inside, or all the vertices can be drawn on the outer face of the embedding. So yeah, that we can say, but for other classes we don't have.
The corresponding densities, that's just the non-signaling densities when you take the first level of the NPA.
Mm-hmm.
I don't see any other questions, so let us thank Peter.